The story of the Tupolev Tu-4 begins not in a Soviet-designed bureau but in the thin, freezing air over Japanese-occupied Manchuria on the afternoon of July 29, 1944. Major Howard Batcher, commander of B-29 Superfortress 42 to 6256 Ramp Rooster, watched his instrument panel flicker as anti-aircraft fire shredded his port engines during a bombing run against the Showa Steel Works in Anshan. With 2 engines dead, hydraulic fluid spraying across the cockpit windshield, and Japanese Zeros circling like sharks, Batcher made a decision that would alter the course of the 20th century. He turned his crippled bomber north toward neutral Soviet territory rather than attempt the 1,200-mile flight back to base in China. 2 other B-29s from the same mission, 42 to 6368, General H. Arnold Special, piloted by Captain Edward L. Freeland, and 42 to 6358, Ding Hao, commanded by Lieutenant William R. McGovern, made the same desperate choice minutes later, their pilots unaware they were flying not toward sanctuary, but into a geopolitical trap that would remain sealed for decades. International law required neutral nations to intern military personnel and equipment from belligerent powers, a standard procedure the Soviets had followed with German and Japanese crews throughout the war. But the B-29 was different. This was not a fighter plane or transport aircraft. It was America's most advanced strategic weapon, a technological marvel whose existence Moscow had only confirmed through grainy reconnaissance photos and fragmentary intelligence reports. Its pressurized cabin, remote-controlled gun turrets, and ability to carry 20,000 pounds of bombs 3,250 miles represented a quantum leap beyond anything in the Soviet arsenal, beyond anything in the world except America's own inventory. When Stalin received the telegram from Vladivostok reporting 3 intact B-29s on Soviet soil, he did not see interned aircraft. He saw a gift from the gods, a chance to leapfrog 5 years of bomber development in a single stroke. Within hours, he issued a directive that bypassed normal military channels and went straight to the Kremlin's inner circle. The aircraft were to be transported immediately to the Tupolev Design Bureau outside Moscow under maximum security. The American crews would be treated as guests in a remote camp near Tashkent, comfortable but isolated, with no communication with the outside world and no indication of how long their hospitality would last. Most critically, Stalin ordered that not a single component of the B-29s was to be returned to the United States. When American diplomats in Moscow politely inquired about the missing bombers weeks later, Soviet Foreign Minister Vyacheslav Molotov offered bland assurances that the aircraft were being safely stored, pending resolution of logistical complexities regarding crew repatriation. The truth, that Stalin had already decided to reverse-engineer the Superfortress down to the last rivet, remained one of the war's best-kept secrets until the Tu-4's dramatic debut 3 years later. For the American crews, the reality of their situation unfolded slowly. They were given comfortable quarters, adequate food, and even recreational facilities. But their guards carried loaded rifles, the perimeter fences were topped with barbed wire, and all mail was censored. When Captain Freeland attempted to send a coded message to U.S. military intelligence through a sympathetic Swiss diplomat, the entire camp was placed under lockdown for 72 hours while NKVD officers interrogated every prisoner individually. The message never reached Washington. Meanwhile, 6,000 miles away, the 3 B-29s began a journey that would transform them from weapons of war into the templates for a new Soviet strategic force. Disassembled in Vladivostok by teams of engineers working under armed guard, the aircraft were loaded onto specially reinforced railway flat cars designed to handle their 70-foot wingspans. The journey to Moscow took 11 days, a slow, deliberate crawl across the Trans-Siberian Railway during which every component was cataloged, photographed, and sealed in climate-controlled containers. Tupolev's lead engineer, Vladimir Petlyakov, traveled with the convoy, sleeping in a converted baggage car filled with engineering drawings and measurement tools. His orders from Stalin were brutally simple. Return to me an exact copy, not similar, not equivalent. Exakt. If one rivet is missing, you will explain why to me personally. Petlyakov understood the subtext. Failure meant the Gulag or worse. The pressure was immense not merely because of Stalin's temper, but because the technical challenge appeared impossible. The B-29 contained over 100,000 individual parts manufactured to tolerances the Soviet aviation industry had never achieved. Its our 3350 duplex Cyclone engines produced 2,200 horsepower each, 50% more than the best Soviet engines of 1944. Its Norden bombsight could place a 500-pound bomb within 75 feet of a target from 20,000 feet, a precision Soviet bombardiers could only dream of. Most daunting was the aircraft's sheer scale. A 141-foot wingspan, 99-foot length, and maximum takeoff weight of 141,000 pounds dwarfed the Soviet Union's largest operational bomber, the Petlyakov Pe-8, which carried less than half the payload over half the distance. Yet, as the flat cars rolled westward across the Siberian taiga, a remarkable transformation was already underway in the minds of the engineers traveling with them. What had seemed impossible began to appear merely difficult, and difficult problems Soviet engineers had learned through decades of industrialization under constraint could be solved through sheer human effort. The B-29 was not magic. It was metal, wire, and glass arranged according to physical laws that applied equally in Moscow and Wichita, Kansas. If Americans could build it, Russians could copy it. The question was not whether it could be done, but whether it could be done before Stalin lost patience, or before America realized what was happening and took countermeasures. That race against time, against technical impossibility, and against the dictator's wrath would consume the next 23 months of Andrei Tupolev's life and ultimately produce not merely a copy but a weapon that would haunt American strategic planners for a generation. The three B-29s that landed in Soviet territory that July day carried no bombs, fired no shots, and killed no enemy soldiers. Yet their arrival may have done more to shape the post-war world than any single combat mission of the entire war. Not because of what they were, but because of what they would become in the hands of engineers working under the shadow of Stalin's terror. When the disassembled B-29s finally reached factory number 22 on the outskirts of Moscow in September 1944, Andrei Nikolaevich Tupolev faced the most daunting challenge of his illustrious career, not because of the technical complexity, but because of the political impossibility of the task Stalin had assigned him. At 67 years old, Tupolev was the Soviet Union's most celebrated aircraft designer, the architect of legendary planes like the AN-T-25 that had set intercontinental distance records in the 1930s and the SB-2 bomber that had dominated Spanish Civil War skies. Yet his position remained precarious despite his fame. In 1938, at the height of Stalin's Great Purge, Tupolev had been arrested on trumped-up charges of wrecking and espionage, sentenced to death, then reprieved at the last moment and sent to a Sharashka, a secret prison design bureau where imprisoned engineers worked under NKVD supervision. For 6 years, Tupolev had designed aircraft while wearing prisoners' clothes, sleeping in a cell, and knowing that a single design flaw could mean execution. Released in 1944 only because the war demanded his expertise, he remained technically a convicted criminal whose rehabilitation depended entirely on delivering results that pleased Stalin. The B-29 project represented both his salvation and his potential doom. Success would restore his reputation, wealth, and freedom. Failure would mean not merely professional disgrace but almost certain death. Stalin had a habit of executing engineers who disappointed him, regardless of past achievements. Tupolev understood this perfectly as he walked through the hangar where the three American bombers sat partially reassembled under bright electric lights. His first order of business was not technical assessment but political theater. He assembled his entire design team, over 200 engineers, draftsmen, and metallurgists, and delivered a speech that would be remembered for decades. Comrades, what stands before us is not an American weapon. It is a challenge to Soviet engineering. Stalin has given us the opportunity to prove that Russian minds can master any technology created by capitalist hands. We will not merely copy this aircraft. We will understand it so completely that we could rebuild it blindfolded. And when we are finished, the world will see that Soviet industry needs no foreign secrets. We absorb them, master them, and transcend them. The speech was pure propaganda, of course. Tupolev knew they would be copying, not transcending. But he needed to frame the project as a patriotic mission rather than industrial espionage to protect his team from accusations of kowtowing to Western technology. A charge that could send any engineer to the Gulag. More practically, he immediately divided the project into 3 parallel streams to accelerate progress. Team Alpha, led by the brilliant but volatile Vladimir Myasishev, would reverse engineer the airframe structure, every spar, rib, and skin panel. Team Beta, under engine specialist Arkady Shvetsov, would dissect the Wright R-3350 engines and develop Soviet equivalents. Team Gamma, headed by weapons expert Vladimir Yermoliev, would analyze the defensive armament system and bomb sight. Each team worked in isolated sections of the factory with armed guards at every doorway. Engineers were forbidden from discussing their work even with colleagues on adjacent teams. This compartmentalization served dual purposes. It prevented leaks to American intelligence, though Moscow didn't yet know the Manhattan Project had already penetrated Soviet atomic research, and ensured that no single engineer possessed enough knowledge to defect with the complete design. The first major crisis erupted within weeks. When Team Alpha began measuring the B-29's aluminum skin panels, they discovered a problem that threatened to derail the entire project. The Americans used a specialized aluminum alloy designated 75ST that simply did not exist in the Soviet Union. Soviet metallurgists had developed their own high-strength aluminum alloys during the war, but none matched the precise combination of tensile strength, fatigue resistance, and weldability that 75ST provided. Tupolev faced a brutal choice: delay the project for years while developing a new alloy from scratch, or substitute an inferior Soviet alloy that might compromise structural integrity at the B-29's extreme operating weights and speeds. He chose a third path, brilliant but risky. He ordered his metallurgy team to analyze shavings from the American skin panels using every available technique. Chemical assays, microscopic examination, even taste tests. Soviet metallurgists of the era sometimes literally tasted metal shavings to detect trace elements. After 3 weeks of round-the-clock work, they identified the critical difference. American 75ST contained precise percentages of zinc, magnesium, and copper that Soviet alloys lacked. But replicating the exact formula proved impossible. The Americans used manufacturing processes involving controlled cooling rates in vacuum chambers that Soviet factories couldn't match. Tupolev's solution revealed his genius. Rather than matching the alloy's composition, match its performance. His team developed a modified version of the Soviet D16T alloy with adjusted heat treatment cycles that achieved nearly identical strength-to-weight ratios despite different chemical composition. The substitution added 127 kilograms to the airframe weight, a penalty Tupolev accepted because it was distributed across thousands of components and wouldn't affect flight characteristics. This decision established a pattern that would define the entire Tu-4 project. Where exact replication was impossible, achieve functional equivalence through Soviet methods. The second crisis emerged from an unexpected source: the aircraft's electrical system. American engineers had designed the B-29 around 115-volt, 400 Hz alternating current, the emerging international standard for military aircraft. The Soviet Union used 220-volt, 50 Hz systems derived from European civilian standards. Converting every generator, transformer, and motor would have required redesigning hundreds of components. Tupolev's solution was characteristically bold. He ordered the entire electrical system copied exactly as American specifications, including voltage and frequency. This meant Soviet factories would have to produce 115V/400 Hz components exclusively for the Tu-4, a logistical nightmare that created spare parts incompatibility with every other Soviet aircraft. But Tupolev calculated correctly. The time saved by avoiding redesign outweighed the long-term maintenance headaches. Stalin wanted results fast, not elegant solutions. The third and most politically dangerous crisis involved the Norden bomb site, the most closely guarded secret in American aviation. When Team Gamma disassembled the unit, they found it booby-trapped with delicate mercury switches designed to destroy critical components if tampered with improperly. 2 junior engineers triggered one such switch during initial examination, ruining the site beyond repair. Panic spread through the team. Stalin had specifically demanded the bomb site be reverse-engineered, and its destruction could be interpreted as sabotage. Tupolev personally intervened, ordering the damaged unit sealed in a lead-lined box and shipped to a secret laboratory where optical specialists would attempt reconstruction from fragments. Meanwhile, he directed his team to design a completely new Soviet bomb site, the OPB-4, that would match the Norden's performance using different principles. This dual-track approach saved the project. When the reconstructed Norden proved unusable, the OPB 4 was ready for installation. But the incident revealed a deeper truth about the copying process. Perfect replication was impossible. Every component presented choices between exact duplication and functional equivalence, between American methods and Soviet capabilities, between theoretical purity and practical necessity. Tupolev's genius lay not in solving these dilemmas perfectly. He often made compromises that added weight or reduced performance, but in making them consistently enough to produce a flyable aircraft on Stalin's impossible schedule. By January 1945, 3 months after the B-29s arrived, Tupolev's teams had completed detailed measurements of over 80,000 components. Every rivet diameter, every wire gauge, every hydraulic fitting had been recorded in massive ledgers filled with hand-drawn diagrams and precise dimensions. Yet they still faced the most daunting challenge of all: converting American inch-pound measurements to metric without introducing cumulative errors that would prevent components from fitting together. One misplaced decimal point in 1,000 measurements could render the entire aircraft unflyable. Tupolev addressed this by creating what he called the golden standard: a single B-29 component, the main wing spar, that would remain in its original American form. Every Soviet-fabricated part would be checked against this standard before installation. If a Soviet-made spar didn't match the American original within 0.1 millimeters, it would be scrapped and remanufactured regardless of cost or time. This obsessive attention to dimensional accuracy would ultimately allow the Tu-4 to achieve its astonishing fidelity to the original, but at a human cost Tupolev rarely discussed. Factory records later revealed that over 1,200 workers were dismissed during the project for quality failures, many sent to labor camps for producing parts that deviated from specifications by less than the width of a human hair. The B-29 had arrived as America's gift to a wartime ally. Under Tupolev's direction, it was being reborn as Stalin's weapon, a perfect copy forged in an atmosphere of terror, where engineering excellence was demanded not for its own sake but as a matter of survival. The conversion from imperial to metric measurements represented the most technically perilous phase of the entire Tu-4 project, a process where abstract mathematics met physical reality in ways that could literally kill test pilots if executed imperfectly. American engineers had designed the B-29 around inch-based dimensions with tolerances often specified to thousandths of an inch, a system that mapped cleanly onto the aircraft's manufacturing processes in Wichita factories where every tool, jig, and fixture had been calibrated for imperial units. Soviet industry operated exclusively in metric, with machine tools graduated in millimeters and micrometers, production standards defined by GOST specifications, and an entire generation of engineers trained to think in base 10 rather than base 12 fractions. The conversion itself seemed straightforward on paper. Multiply inches by 25.4 to obtain millimeters. But reality proved far more complex. Consider a simple structural component like a wing rib, a stamped aluminum piece with dozens of holes for rivets, lightning cutouts to reduce weight, and flanges for attachment to adjacent ribs. The American drawing might specify a hole diameter of 0.1875 inches, 3/16 inch, a dimension easily drilled with standard American tooling. Converted to metric, this became 4.7625 millimeters, a dimension requiring specialized drill bits that didn't exist in Soviet factories. The obvious solution, rounding to 4.8 millimeters, seemed harmless for a single hole. But the B-29 contained over 18,000 rivet holes in its wings alone. If every hole were enlarged by 0.0375 millimeters to accommodate standard metric drill bits, the cumulative effect would be catastrophic. Wing skin panels wouldn't align properly, structural loads would concentrate at mismatched joints, and fatigue cracks would propagate through the airframe during flight. Tupolev's team confronted this problem systematically. They created conversion tables that preserved functional relationships rather than performing blind arithmetic. A 3/16 inch rivet became a 4.8 millimeter rivet not because 0.1875 times 25.4 is equal to 4.7625, but because Soviet industry already manufactured 4.8 millimeter rivets that provided equivalent shear strength. Critical dimensions, like the diameter of the main landing gear axle that carried 70,000 pounds of landing load, were converted with extreme precision using custom-made tooling. Non-critical dimensions, like the spacing of interior cabin rivets, were rounded to nearest metric equivalents to simplify manufacturing. This selective precision approach saved thousands of hours of tooling development while maintaining structural integrity. Yet, even with meticulous conversion tables, cumulative errors threatened the project daily. When the first Soviet-fabricated wing section was assembled in March 1945, engineers discovered a 3.2mm misalignment between the leading edge skin and the main spar, a gap small enough to be invisible to casual inspection but large enough to create dangerous aerodynamic flutter at high speeds. Disassembly revealed the culprit: a chain of 5 separate conversions where each component had been manufactured at the extreme edge of its tolerance band. Individually, each part met specifications. Collectively, they created an unacceptable assembly error. Tupolev responded with characteristic ruthlessness. He ordered the entire wing section scrapped, a loss of 47,000 man-hours of labor and 3.2 tons of scarce aluminum alloy. More significantly, he mandated a new quality control procedure. Every component would be measured not just against its drawing, but against the actual American part it was replacing. Factory number 22 installed over 200 precision measurement stations where inspectors used calibrated gauges to compare Soviet parts against American originals before release to assembly lines. Workers who produced out-of-tolerance parts faced immediate dismissal. Foremen responsible for defective batches received demotions or worse. The pressure created a culture of obsessive precision that bordered on paranoia. Engineers carried personal micrometers to verify measurements independently. Machinists checked tool wear after every 10th part rather than following standard maintenance schedules. Quality inspectors worked 12-hour shifts examining components under magnifying lenses, searching for microscopic deviations that might compromise flight safety. This intensity produced remarkable results. By summer 1945, Soviet factories were producing B-29 components with dimensional accuracy matching or exceeding American manufacturing tolerances. But the human cost mounted steadily. NKVD reports from the period document 87 worker suicides at factories involved in the 2-4 project. Men and women who chose death over the shame of producing defective parts that might cause a crash and bring Stalin's wrath upon their families. The electrical system conversion presented even greater challenges than structural components. American wire gauges followed the AWG, American wire gauge, standard where lower numbers indicated thicker conductors, a counterintuitive system that defied simple metric conversion. A 12-gauge wire carried a specific current load based on its cross-sectional area of 3.31 square millimeters. Soviet GOST standards specified wires by actual cross-section: 3.0 mm superscript 2, 4.0 mm superscript 2, 5.5 mm superscript 2. Neither matched American sizes exactly. Tupolev's electrical team solved this by creating hybrid specifications: wires manufactured to Soviet cross-sections but labeled with American gauge numbers to prevent assembly errors. This created a bizarre situation where Soviet electricians installing wiring in the 2-4 worked with components physically identical to Soviet standards but marked with American nomenclature. A cognitive dissonance that caused frequent errors until workers memorized the conversion tables. More critically, the B-29's complex electrical architecture, over 120 miles of wiring controlling everything from gun turrets to cabin pressurization, required precise impedance matching to prevent signal degradation and electromagnetic interference. American engineers had designed the system assuming specific resistivity values for copper wire manufactured to ASTM standards. Soviet copper contained slightly different trace impurities that altered electrical properties. Rather than purify the copper to American standards, a prohibitively expensive process, Tupolev's team redesigned circuit layouts to compensate for the differences, adding resistors and capacitors at strategic points to maintain signal integrity. These modifications added weight and complexity but preserved functionality. The propulsion system conversion proved most challenging of all. The Wright R3350 duplex cyclone was arguably the most complex piston engine ever mass-produced. A 3,447 cubic inch radial engine with 18 cylinders arranged in 2 rows, twin superchargers, and intricate cooling systems that had plagued American B-29s with engine fires throughout 1944. Soviet engineers initially hoped to simply copy the engine as Shvetsov's team had done with airframe components. But metallurgical analysis revealed another showstopper. The R3350's crankshaft was forged from a specialized nickel-chromium molybdenum steel alloy that Soviet metallurgy couldn't replicate. Attempts to substitute Soviet alloys resulted in crankshafts that fractured under test conditions after fewer than 50 hours of operation. Unacceptable for an aircraft expected to fly 3,000-hour service lives. Shvetsov proposed an audacious solution. Reverse engineer not the American engine, but its underlying principles, then design a new Soviet engine, the Ash-73TK, that achieved equivalent power output using Soviet materials and manufacturing methods. This meant accepting certain performance penalties. The Ash-73TK weighed 110 kilograms more than the R-3350 and consumed 7% more fuel at cruise power. But it was reliable, manufacturable, and crucially, producible in Soviet factories without exotic materials. Stalin initially rejected the proposal, demanding an exact copy. Only after Tupolev personally intervened, arguing that engine failure would crash the prototype and kill test pilots, bringing the entire project to a halt, did Stalin relent. The compromise revealed a fundamental truth about the Tu-4 project. Perfect replication was impossible. Every system required adaptation to Soviet industrial reality. The art lay in making these adaptations invisible to anyone examining the finished aircraft from the outside. By late 1945, as the first complete Tu-4 airframe took shape in Factory No. 22's main assembly hall, Tupolev's teams had solved hundreds of such adaptation challenges. The aircraft emerging from the assembly line was 99.9% dimensionally identical to the B-29 that had landed in Vladivostok 16 months earlier, but beneath that identical skin lay thousands of subtle modifications reflecting Soviet engineering choices, material substitutions, and manufacturing compromises. The most famous example involved the aircraft's lavatory. American B-29s featured a small chemical toilet in the rear fuselage with an English-language warning label, "Caution! Seat must be closed during flight." When Soviet workers prepared to install the Soviet-made toilet assembly, they discovered their version lacked the warning label. Tupolev faced a dilemma. Adding the label would require custom printing plates and adhesive formulations, delaying production by weeks. Omitting it might seem trivial, but Stalin had demanded exact replication down to the smallest detail. Tupolev's solution became legendary in Soviet aviation circles. He ordered the English warning label reproduced exactly as on the American aircraft, including the specific font and even minor printing imperfections visible under magnification. When questioned why Soviet bombers needed English warnings, Tupolev reportedly replied, "Stalin said copy every rivet. A warning label is smaller than a rivet. Do not make me explain to him why we copied the rivets but not the words." The anecdote, whether apocryphal or true, captured the project's defining characteristic: an obsession with surface fidelity masking profound underlying adaptations. The Tu-4 taking shape in that Moscow factory was neither pure copy nor original design. It was something new entirely. A Soviet aircraft wearing an American skin, its identity suspended between two worlds, its purpose shaped not by engineering elegance but by Stalin's paranoia and America's wartime generosity. As winter 1945 turned to spring 1946, the first prototype approached completion. Tupolev knew the real test was coming, not dimensional accuracy or ground systems checks, but the moment when test pilot Mikhail Nuktikov would push the throttles forward and commit 60 tons of metal, fuel, and human lives to the unforgiving physics of flight. No amount of measurement precision could guarantee that moment would end in triumph rather than catastrophe. The copied aircraft would have to prove itself not on paper, but in the sky. The first flight of the Tu-4 prototype on May 19, 1947, unfolded not as a triumphant public spectacle but as a tightly controlled secret operation conducted under conditions of extreme tension that revealed the project's precarious status even at its moment of apparent success. Factory No. 22's airfield outside Moscow had been sealed for weeks under NKVD supervision. Every civilian within 5 kilometers forcibly relocated, every approaching road blocked by armed patrols, every building on the perimeter occupied by snipers with orders to shoot unauthorized observers on sight. The secrecy reflected Stalin's dual anxieties: fear that American intelligence might photograph the aircraft before its capabilities were fully understood, and deeper fear that the flight might end in disaster, exposing the entire project as a colossal waste of resources that would demand scapegoats. Tupolev himself stood on the control tower balcony wearing a heavy overcoat despite the spring warmth. his face pale and drawn after 72 hours without sleep. Beside him stood Air Marshal Alexander Golovanov, commander of Soviet long-range aviation, who had staked his career on the Tu-4's success. Between them hung an unspoken understanding. If the aircraft crashed, both men would face execution regardless of technical explanations. Below them on the tarmac, test pilot Mikhail Nuktikov completed his pre-flight inspection with methodical calm that masked profound apprehension. Nuktikov was one of the Soviet Union's most experienced test pilots, a veteran of over 300 experimental aircraft flights who had survived crashes that would have killed lesser men. Yet he had confided to his wife the night before that this flight frightened him more than any other. "I am flying an American aircraft built by Soviet hands using Soviet materials. If one conversion error exists, if one metric substitution created a resonance frequency the Americans never encountered, this airplane will tear itself apart at 20,000 feet where no parachute can save me." His fears were not irrational. American B-29s had suffered catastrophic structural failures during early testing when harmonic vibrations at specific airspeeds caused tail sections to detach mid-flight. Soviet engineers had studied these failures through captured technical manuals and believed they had incorporated the necessary reinforcements. But belief was not certainty. At 9:47 hours, Nuktikov signaled readiness. Tupolev gave a barely perceptible nod. The four Ash-73 TK engines coughed to life, their 18 cylinders each firing in precise sequence to produce 8,800 horsepower of thrust. A sound deeper and rougher than the American R-3350s, but unmistakably powerful. Taxiing to the runway threshold, Nuktikov performed final control checks, his hands moving over yoke and throttles with practiced precision. At 9:58, he released the brakes and advanced the throttles to take off power. The Tu-4 began its roll down the 3,000-meter concrete strip, its 141,000-pound weight requiring every meter of available runway. At 165 kilometers per hour, Nuktikov eased back on the yoke. The aircraft lifted smoothly, its nose rising toward the sky with a grace that surprised even its designers. For the first 3 minutes, everything appeared perfect. The aircraft climbed through 1,000 meters, then 2,000, then 5,000 meters without unusual vibrations or control difficulties. Nuktikov radioed standard reports, all systems nominal, cabin pressurization stable, engine temperatures within limits. Tupolev allowed himself a faint smile, the first in weeks. Then, at 6,200 meters, disaster struck. A violent shudder ran through the airframe. Not the smooth buffet of turbulence, but a sharp, metallic vibration that rattled instruments in their panels and made the control yoke jump in Nuktikov's hands. The aircraft's nose pitched down abruptly, then snapped up, then rolled 10 degrees to port before Nuktikov wrestled it back to level flight. On the ground, Tupolev's smile vanished. He recognized the symptoms instantly: aeroelastic flutter in the horizontal stabilizer, the same phenomenon that had destroyed early B-29s. American engineers had solved it by adding mass balances to the elevator hinges, but Soviet weight-saving substitutions had omitted these components as non-essential. Nuktikov fought the controls with desperate strength, his arms trembling with the effort. The vibration intensified, threatening to shake the tail section apart. In that moment of crisis, his training overrode panic. He reduced power on engines 3 and 4 to break the harmonic resonance, simultaneously extending the landing gear to increase drag and disrupt airflow over the tail surfaces. The violent shaking subsided to a manageable buffet. Nuktikov, his flight suit soaked with sweat despite the cold cockpit air, began a cautious descent. He would not attempt to return to the factory airfield, too risky with compromised controls. Instead, he aimed for a secondary airfield 40 kilometers north with longer runways and emergency equipment. The descent took 23 agonizing minutes. Each altitude change risked reigniting the flutter. Nuktikov maintained precise airspeed control, his eyes flicking constantly between airspeed indicator and artificial horizon. At 500 meters altitude on final approach, the vibration returned briefly but subsided as he crossed the threshold. The landing was hard but controlled, a 4.2G touchdown that stressed the airframe but kept the aircraft in one piece. As the Tu-4 rolled to a stop, emergency crews swarmed around it. Nuktikov shut down the engines and sat motionless for a full minute before unstrapping and climbing down the crew ladder. His legs buckled as he reached the tarmac. Ground crew caught him before he fell. Tupolev arrived by staff car 15 minutes later, his face ashen. He walked straight to Nuktikov without acknowledging anyone else. "What happened?" he demanded. Nuktikov described the flutter sequence with technical precision. Tupolev listened silently, then turned without a word and walked to the aircraft's tail section. He ran his hands over the elevator hinges, feeling for the missing mass balances his team had deemed unnecessary. When his fingers found only smooth metal where American drawings showed counterweights, he closed his eyes for a long moment. Back at factory number 22 that evening, the atmosphere was funereal despite the aircraft's survival. Stalin had been informed of the incident within minutes. His response was characteristically brutal. "Fix it in 30 days or I will have the entire design team shot." Tupolev gathered his senior engineers in a soundproofed conference room and delivered a speech devoid of his usual inspirational rhetoric. "Comrades, we have failed Stalin's trust, but we will not fail his deadline. Every engineer who worked on the tail assembly will work 16-hour shifts until the problem is solved. We will install mass balances identical to the American design. No substitutions, no improvements, no Soviet innovations. We will copy exactly what the Americans did because their solution works and ours does not. Anyone who objects to this approach may explain his objections to Stalin personally." The threat was unnecessary. Everyone understood the stakes. For the next 28 days, factory number 22 operated as a single organism focused on one task: redesigning, manufacturing, and installing mass-balanced elevator hinges on all 324 prototypes. Tupolev slept in his office, emerging only to inspect progress at critical milestones. Nuktikov, despite his traumatic experience, volunteered to fly the second test flight on June 18th, knowing that refusal would be interpreted as cowardice with fatal consequences for his family. This time, the flight proceeded without incident. The aircraft climbed to 10,000 meters, performed standard maneuverability tests, and returned to base after a 3-hour flight that validated the flutter fix. Stalin, informed of the successful flight, sent a terse telegram: "Acceptable. Proceed to production." The word acceptable, rather than excellent or outstanding, revealed his lingering displeasure, but it was enough to save Tupolev's life and the project's future. Yet the first flight's near disaster exposed a deeper truth about reverse engineering. Copying dimensions does not guarantee copying performance. The B-29's design embodied thousands of lessons learned through American testing failures, lessons documented in technical manuals but not always understood by Soviet engineers reading translations. Mass balances on elevator hinges seemed like minor details until their absence nearly killed a test pilot. Similar hidden knowledge lurked throughout the design. Specific rivet patterns that distributed stress during turbulence, precise cable tensions that prevented control surface oscillation, even the exact viscosity of hydraulic fluid that ensured smooth operation at -50 degrees Celsius. Each represented a potential failure point where Soviet substitutions might prove catastrophic. Tupolev responded by instituting what he called American fidelity audits. Teams of engineers who compared every Soviet component not just to dimensional drawings, but to actual performance data from American test reports smuggled out of US military libraries by Soviet intelligence assets. When discrepancies emerged, Tupolev increasingly chose exact replication over Soviet adaptation, a decision that added weight and complexity but reduced risk. The Tu-4 that entered production in late 1947 was therefore even more faithful to the B-29 than the first prototype, its designers having learned through near tragedy that some American engineering choices reflected hard-won wisdom rather than arbitrary preferences. This painful education came at human cost beyond Nuktikov's terror. 3 ground crew members died in a fire during engine testing when a fuel line substitution failed under pressure. 2 engineers committed suicide after quality control rejected their components for microscopic dimensional errors. 1 factory manager was arrested by the NKVD and never seen again after reporting unavoidable delays in his section's production schedule. The Tu-4's development thus unfolded not as a triumph of engineering, but as a testament to human endurance under tyranny. a project where success required not merely technical skill but willingness to sacrifice everything, including one's life, for Stalin's whim. When the first production 2-4 rolled off the assembly line in October 1947, it represented both a miracle of industrial replication and a monument to terror. Its flawless exterior concealed not just metric conversions and material substitutions, but the blood, fear, and desperation of thousands who had labored under threat of death to give Stalin his American bomber. The aircraft was ready for service, but its true test would come not in Soviet skies, but when American eyes finally saw it and realized with horror that their most advanced weapon had been duplicated by an enemy they believed technologically inferior. The moment of revelation arrived not through intelligence reports or defector testimony, but through sheer visual shock at the Tushino Air Show near Moscow on August 3, 1947. A carefully choreographed propaganda spectacle that would trigger panic in Washington and reshape Cold War strategy overnight. Stalin had personally approved the 2-4's public debut after months of debate within the Politburo. Hardliners like Lavrentiy Beria argued for continued secrecy, fearing American countermeasures if the bomber's capabilities became known. Foreign Minister Molotov warned that revealing the copy might provoke diplomatic crisis with the United States, still technically an ally despite growing tensions. But Stalin, ever the theatrical dictator, recognized the psychological value of demonstrating Soviet technological parity at the precise moment when American officials were publicly boasting about their nuclear monopoly. The air show itself was a masterpiece of Soviet stagecraft. Over 500,000 spectators packed the viewing areas, party officials in reserved sections near the reviewing stand, factory workers bussed in from Moscow's industrial districts, foreign diplomats clustered under a special pavilion with interpreters and refreshments. The program followed a carefully scripted sequence designed to build anticipation. First, formations of Yak-3 fighters performing aerobatic maneuvers, then Il-2 Sturmovik ground attack aircraft demonstrating rocket attacks on mock targets. Finally, a squadron of Tu-2 medium bombers flying in tight formation. The crowd's applause grew with each act, but seasoned observers noticed Stalin's impatience. He kept checking his watch, his jaw tight with anticipation. Then, at precisely 14:30 hours, the announcer's voice boomed across the field, "Comrades, the final demonstration of Soviet aviation might." For aircraft appeared on the western horizon, silhouettes too large to be fighters, too sleek to be transports. As they drew nearer, experienced aviation journalists in the foreign press section exchanged puzzled glances. The aircraft were unmistakably B-29 Superfortresses, but America had never sold or transferred B-29s to the Soviet Union. American diplomats present, Ambassador Walter Bedell Smith among them, initially assumed they were witnessing captured Japanese aircraft or perhaps Lend-Lease B-24s modified beyond recognition. Then the lead aircraft banked slightly, catching the sun on its fuselage. Through binoculars, Smith saw the Red Star insignia, and beneath it, Cyrillic lettering identifying the aircraft as 2-4. His blood ran cold. He knew instantly what this meant. The Soviets had somehow acquired B-29s and reverse-engineered them with astonishing speed. The formation executed a perfect flyby at 300 meters altitude, close enough for spectators to see details. The distinctive twin-tail fins, the 4 massive engines, the glazed bombardier's nose. Then, in a maneuver that defied belief, the lead aircraft peeled off from the formation and executed a series of steep turns and climbs that demonstrated performance matching or exceeding American B-29 capabilities. The crowd erupted in thunderous applause. Stalin rose from his seat, a rare public display of emotion, and waved to the pilots as they passed overhead. For the Soviet people, the display was pure triumph, a symbol that their nation had not merely survived the war but emerged technologically equal to the capitalist superpower. For the Americans watching, it was a strategic earthquake. Ambassador Smith composed a coded cable to Washington within minutes of returning to his embassy. For B-29 equivalents flown today at Tushino.
Désignation Tu-4.
Performance appears identical to Superfortress. Assessment: Soviets possess operational intercontinental bomber capability years ahead of estimates. Recommend immediate reassessment of strategic vulnerability. The cable reached President Truman's desk the following morning. His reaction, recorded by aides, was a single muttered expletive followed by, "How the hell did they get those?" The question launched a frantic intelligence investigation that would consume CIA resources for months. Initial theories ranged from plausible to paranoid. Perhaps the Soviets had captured B-29s shot down over Japan. Maybe American communists had smuggled blueprints out of Boeing factories. Possibly German engineers captured after the war had provided design knowledge. The truth, the 3 emergency landings in 1944, remained hidden because American military records classified those incidents as routine internments not requiring high-level notification. No one in Washington had connected 3 missing bombers from a single mission to a strategic threat 3 years later. The intelligence failure was catastrophic in its implications. American nuclear strategy since 1945 had rested on one unshakable assumption. The United States possessed a temporary monopoly on deliverable atomic weapons because no adversary had bombers capable of reaching American soil. The B-36 Peacemaker, the only American bomber with true intercontinental range, was still in limited production. The B-29 could reach the Soviet Union only from forward bases in Europe or Asia, bases vulnerable to preemptive attack. Now, overnight, that calculus inverted. If the Soviets possessed B-29 equivalents, and early intelligence estimates suggested they might have dozens already in service, they could potentially deliver atomic bombs to American cities from bases deep inside the USSR, beyond the reach of American fighters. The psychological impact on American strategic planners proved even more profound than the technical threat. General Curtis LeMay, commander of Strategic Air Command, reportedly slammed his fist on a conference table during an emergency meeting. "We assumed we had until 1955 before they developed a strategic bomber. This changes everything. Everything." SAC immediately accelerated B-36 production, ordered round-the-clock bomber patrols along Arctic approaches to North America, and began planning preemptive strikes against suspected 2-4 bases, a doctrine of preventive war that would dominate American strategy until the Soviet atomic test in August 1949 made such plans suicidal. More subtly, the 2-4's appearance shattered American technological complacency. Since the Wright brothers' first flight, the United States had led aviation innovation, a lead seemingly confirmed by the B-29's dominance in the Pacific War. The 2-4 demonstrated that Soviet engineers could not merely copy but master advanced Western technology with frightening speed. This realization triggered what historians call the Sputnik panic before Sputnik, a crisis of confidence that would fuel massive American investments in aerospace research, ultimately producing the X-planes, the U-2 spy plane, and eventually the space program. Soviet intelligence quickly grasped the psychological victory they had achieved. Within weeks of the Tushino display, Soviet media began publishing carefully staged photographs of 2-4s with nuclear bomb shapes loaded in their bomb bays, though the USSR wouldn't test its first atomic device until August 1949. The implication was deliberate and devastating. America's atomic monopoly was already obsolete. American intelligence analysts, lacking reliable information about Soviet nuclear progress, couldn't disprove the claim. For 2 years, American policymakers operated under the terrifying assumption that Stalin might possess both the bomb and the means to deliver it to American cities, a fear that justified massive defense spending and aggressive containment policies that might otherwise have seemed excessive. The 2-4's strategic impact thus extended far beyond its actual capabilities. In reality, the aircraft faced severe limitations that Soviet propaganda carefully concealed. Its range of 5,400 kilometers fell short of true intercontinental reach, insufficient to strike the continental United States from Soviet bases without one-way missions or risky aerial refueling, a technology the USSR hadn't yet mastered. Its payload capacity of 3,000 kilograms could carry early Soviet atomic bombs, but barely. The RDS-1 device tested in 1949 weighed 4,500 kilograms, requiring modifications that further reduced range. Most critically, Soviet navigation technology lagged years behind American systems. 2-4 crews lacked the precision to reliably find American cities at night or in bad weather, let alone specific military targets. Yet these limitations mattered less than the perception of capability. In the psychological warfare of the early Cold War, the 2-4 functioned as what strategists call a capability signal, a demonstration that the Soviet Union possessed the industrial and technical capacity to master any Western technology given time. If they could copy the B-29 in 2 years, what else could they replicate? Jet engines? Radar? Atomic weapons? The Tu-4 became a symbol of Soviet technological inevitability, a message that resonated deeply in Washington precisely because American leaders understood the immense difficulty of the copying feat. They knew the B-29 represented the pinnacle of 1940s aviation technology. They knew reverse engineering it without blueprints required extraordinary skill. They knew achieving flight readiness in 23 months demanded industrial mobilization on a staggering scale. The very impressiveness of the achievement made it terrifying. American intelligence agencies responded with unprecedented urgency. The newly formed CIA launched Operation Moolah, a program offering $100,000 and political asylum to any Soviet pilot who defected with a Tu-4. Reconnaissance flights along Soviet borders intensified, with American pilots risking anti-aircraft fire to photograph Tu-4 bases and count aircraft on ramps. Most significantly, the U.S. Air Force accelerated development of interceptors capable of engaging high-altitude bombers. The F-86D Sabre and F-94 Starfire entered service years ahead of original schedules specifically to counter the Tu-4 threat. This arms race dynamic, perception-driving reality became a defining feature of the Cold War. The Tu-4 itself never dropped a bomb in anger, never flew a combat mission, never came closer than 5,000 kilometers to American soil. Yet its existence forced America to spend billions on defenses against a threat that was more symbolic than actual, diverted resources from other military priorities, and created a climate of fear that justified policies of massive retaliation and brinkmanship. The bomber's greatest weapon was not its payload, but its psychological impact, a weapon Stalin understood perfectly when he approved its public debut. He knew that in the new atomic age, perception of capability often mattered more than capability itself. By demonstrating that the Soviet Union could match American technology through sheer will and industrial effort, the Tu-4 shattered the illusion of American invulnerability that had underpinned post-war confidence. The age of American security behind two oceans had ended not with a bang but with the roar of 4 copied engines over a Moscow airfield, a sound that echoed across continents and announced the bipolar world to come. For Andrei Tupolev, the Tikhino display brought personal vindication. Stalin summoned him to the Kremlin the following day and awarded him the Hero of Socialist Labor Medal, the Soviet Union's highest civilian honor, along with a dacha outside Moscow and a Zeiss limousine. More importantly, his 1938 conviction was formally expunged. He was restored to full membership in the Communist Party and given unlimited resources for future projects. The man who had designed aircraft as a prisoner now stood as Soviet aviation's undisputed patriarch, a transformation made possible by his willingness to copy rather than innovate, to serve Stalin's whim rather than engineering purity. As he accepted the medal, Tupolev understood the irony perfectly. His greatest achievement was not creating something new, but reproducing something old with such fidelity that it terrified the nation that had invented it. The Tu-4 had made him a hero, but it had also set a precedent that would haunt Soviet aviation for decades. The belief that copying Western technology could substitute for indigenous innovation, that reverse engineering could replace fundamental research. This mindset would eventually cripple Soviet aerospace development when the West moved beyond technologies worth copying. But in 1947, none of that mattered. The bomber flew. Stalin was pleased. America was afraid. For Tupolev, that was victory enough. The operational reality of the Tu-4 fleet revealed a stark contrast between propaganda imagery and the harsh limitations that constrained its actual military utility. A gap between Stalin's strategic ambitions and the aircraft's technical shortcomings that Soviet commanders navigated through improvisation, secrecy, and sheer force of will. By 1950, Soviet long-range aviation operated 847 Tu-4 bombers organized into 12 heavy bomber divisions, a force that appeared on paper to rival America's Strategic Air Command in size if not sophistication. Yet beneath the impressive numbers lay profound operational constraints that rendered the fleet strategically marginal despite its psychological impact on Western planners. The most fundamental limitation was range. The B-29 had been designed for Pacific operations with forward bases in China and the Marianas Islands, missions rarely exceeding 3,200 kilometers round trip. The Tu-4 inherited this design philosophy, but faced a radically different strategic geography. To threaten meaningful American targets, Soviet bombers needed to fly 8,000 to 10,000 kilometers round trip from bases in European Russia or Siberia. Even with maximum fuel loads and minimal bomb weight, the Tu-4's combat radius barely reached 2,700 kilometers, sufficient to strike London or Paris from Soviet territory, but utterly incapable of reaching the continental United States. Soviet planners understood this limitation perfectly yet concealed it from Stalin through carefully crafted briefing documents that emphasized theoretical maximum range under ideal conditions rather than realistic combat radius with full payload. When Stalin demanded plans for bombing New York City, Air Marshal Golovanov presented a scheme involving one-way missions with crews parachuting into the Atlantic after weapon release. A suicide tactic that horrified operational commanders but satisfied the dictator's desire for symbolic capability. More practical missions focused on European NATO targets, RAF bases in England, nuclear facilities in France, port facilities in West Germany. Yet even these missions faced daunting challenges. Western Europe lay within range, but penetrating NATO airspace required surviving layers of air defense that had evolved dramatically since 1945. By 1950, Britain operated an integrated radar network covering its entire airspace, backed by Gloucester Meteor and de Havilland Vampire jet fighters capable of intercepting 2-4s at their 10,000-meter operational altitude. American F-86 Sabres stationed in West Germany could reach Mach 0.9, significantly faster than the 2-4's maximum speed of 558 kilometers per hour. Soviet intelligence assessments concluded that unescorted 2-4 formations would suffer 70 to 90% losses attempting to penetrate Western European airspace, a casualty rate that would annihilate the entire fleet after 2 or 3 missions. The solution, fighter escorts, proved equally problematic. Soviet jet fighters of the era, like the MiG-15, possessed superior speed and climb rate but lacked the range to accompany 2-4s beyond the Iron Curtain. Proposals to develop dedicated long-range escort fighters consumed engineering resources without yielding practical results until the mid-1950s. Consequently, 2-4 operations remained confined to training exercises over Soviet territory and symbolic deployments to forward bases in Poland and East Germany, positions that placed Western European targets within range but also placed the bombers within range of NATO preemptive strikes. This vulnerability created a strategic paradox. The 2-4 fleet was too valuable to risk in actual combat yet too threatening to leave undefended, forcing the Soviet Union to invest heavily in air defense systems to protect bombers that could not effectively strike back. The aircraft's payload limitations compounded these range problems. Early Soviet atomic bombs, the RDS-1 tested in 1949 and RDS-2 in 1951, weighed 4,500 to 5,000 kilograms, exceeding the 2-4's maximum single bomb capacity of 3,000 kilograms. Soviet engineers responded with 2 stopgap solutions. Either modify bomb bay doors and structural supports to accommodate the overweight weapons, reducing range by 15% due to increased drag and weight, or develop smaller warheads that fit standard bomb bays but sacrificed yield. The first 2-4 nuclear-capable variant, designated 2-4A, entered service in 1951 after extensive structural reinforcement that added 1,200 kilograms to empty weight. Even then, the aircraft could carry only one RDS-3 bomb weighing 3,000 kilograms with a yield of 42 kilotons, powerful but less than half the yield of contemporary American weapons. More critically, the 2-4 lacked an accurate bomb sight capable of placing nuclear weapons on target from high altitude. The Soviet OPB-4 bomb sight copied from the Norden design proved unreliable in operational conditions, with circular error probable exceeding 2,000 meters at 10,000 meters altitude, unacceptable for nuclear weapons where accuracy directly determined destructive effect. Soviet crews compensated through brute force tactics. Instead of precision strikes, they planned area bombing of entire cities, accepting that most weapons would miss intended aim points but hoping blast effects would still cause catastrophic damage. This approach required large numbers of bombers, dozens per target, to ensure destruction, further straining the limited 2-4 fleet. Crew training revealed equally severe limitations. American B-29 crews received up to 18 months of specialized training before combat deployment, including extensive navigation practice over featureless ocean, high-altitude bombing drills, and formation flying exercises. Soviet 2-4 crews received 6 months of training on average, with minimal night flying or adverse weather practice. Navigation training proved particularly deficient. Soviet crews relied primarily on dead reckoning and celestial navigation, techniques that worked adequately over the featureless expanses of Siberia, but failed catastrophically over cloudy European skies or featureless ocean. During a 1952 exercise simulating a strike against London, 60% of participating 2-4s failed to find their targets within 50 kilometers, with several crews becoming completely lost and requiring radio homing signals to return to base. These deficiencies remained hidden from Western intelligence through obsessive Soviet secrecy. 2-4 bases operated under conditions of extreme isolation, fences topped with barbed wire and broken glass, guard towers every 200 meters, strict prohibition on unauthorized photography. Crews lived in closed compounds with no contact with local populations. Families were housed in separate barracks to prevent information leakage through domestic conversations. Maintenance occurred in enclosed hangars with windows blacked out. Even routine engine runs were scheduled for nighttime hours to minimize acoustic detection by Western listening posts. This secrecy created an intelligence vacuum that Western analysts filled with worst-case assumptions. Without reliable data on 2-4 capabilities, NATO planners assumed the aircraft possessed performance equal to or exceeding the B-29, a reasonable assumption given the aircraft's visual fidelity, but one that vastly overestimated its operational effectiveness. American intelligence estimates in 1950 credited the 2-4 fleet with 90% mission-capable rate, 4,000-kilometer combat radius with nuclear payload, and navigation accuracy within 500 meters at 10,000 meters altitude, assessments that were 30 to 100% more optimistic than reality. This intelligence failure had profound strategic consequences. NATO allocated disproportionate resources to air defense against a threat that was far less capable than believed, diverting fighter squadrons from other missions, accelerating radar network construction, and justifying expensive interceptor programs that might have been scaled back with accurate intelligence. More significantly, the perceived 2-4 threat accelerated American development of thermonuclear weapons and intercontinental ballistic missiles, technologies pursued partly to overcome the bomber gap that didn't actually exist. The 2-4 thus functioned as a strategic phantom, its actual capabilities limited but its perceived threat enormous, driving Western military spending and technological development far beyond what rational assessment would have justified. Soviet commanders understood this dynamic perfectly and exploited it deliberately. They staged carefully choreographed displays of 2-4 strength, mass formation flyovers during May Day parades, deployments to forward bases coinciding with NATO exercises, even controlled leaks to sympathetic journalists about new modifications that didn't exist. Each demonstration reinforced Western perceptions of Soviet bomber strength while costing the USSR minimal resources. The most audacious deception occurred in 1954 when Soviet intelligence learned that American U-2 spy planes were preparing their first overflights of Soviet territory. Rather than hide the 2-4 fleet, Air Marshal Golovanov ordered all serviceable aircraft concentrated at 3 bases near Moscow and Leningrad, creating the illusion of massive bomber strength precisely where American cameras would photograph them. The resulting U-2 imagery showed hundreds of 2-4s parked wingtip to wingtip, convincing American analysts that the Soviet Union possessed a far larger strategic bomber force than reality. In truth, many photographed aircraft were non-flyable hangar queens, maintained for appearance only. Others were dummies constructed from wood and canvas. But the deception succeeded brilliantly. American intelligence overestimated Soviet bomber strength by 300% until satellite reconnaissance in the early 1960s revealed the truth. This pattern of strategic deception, using the 2-4 as a prop in psychological warfare rather than a genuine weapon system, defined the aircraft's operational history. The fleet never flew a combat mission beyond limited use in the Korean War, where a handful of 2-4s conducted nocturnal harassment raids against South Korean airfields with minimal effect, and never came closer than training ranges to actual nuclear targets. Yet its existence shaped Cold War strategy more profoundly than many weapons that saw actual combat. By convincing America that the Soviet Union possessed credible intercontinental strike capability years before it actually did, the 2-4 accelerated the arms race, justified massive defense spending, and created a climate of mutual fear that defined superpower relations for decades. The aircraft's greatest impact was not what it could do, but what Western planners believed it could do. A testament to Stalin's understanding that in nuclear strategy, perception often matters more than reality. For the men who flew and maintained the 2-4, this strategic abstraction meant little compared to daily hardships. Crews endured primitive conditions at remote bases, unheated barracks, inadequate medical care, food shortages during harsh winters. Maintenance crews worked 14-hour shifts in unheated hangars, their fingers numb as they serviced complex systems with inadequate tools. Engine mechanics faced particular hardship. The ASH-73TK engines required meticulous care to prevent the catastrophic fires that plagued early operations, yet spare parts were scarce and factory support slow. Despite these conditions, morale remained surprisingly high among Tu-4 personnel. They understood they operated the Soviet Union's most prestigious aircraft, a symbol of national achievement that carried Stalin's personal blessing. Promotion opportunities were excellent for successful crews. Material rewards substantial by Soviet standards. More importantly, they believed in their mission, genuinely convinced that their bombers deterred American aggression and protected the socialist homeland. This conviction sustained them through hardships that would have broken less ideologically committed forces. When the first Soviet thermonuclear weapon was successfully tested in August 1953, Tu-4 crews celebrated as if they had personally achieved the breakthrough. Their aircraft would deliver these weapons, making them central to Soviet security. The illusion would not last. By 1955, newer aircraft like the turboprop Tu-95 Bear and jet-powered Maya-4 Bison began replacing the Tu-4 in frontline units. The piston-engine bomber that had terrified Washington 8 years earlier was now obsolete, not because it failed technically, but because aviation technology had advanced beyond its design philosophy. Yet, even in retirement, the Tu-4 continued serving Soviet strategy. Many airframes were converted to specialized roles. Airborne early warning platforms with radomes mounted above fuselages, electronic intelligence collectors packed with signal interception equipment, even motherships for experimental parasite fighters. These second careers extended the aircraft's service life into the 1960s, ensuring that Stalin's copied bomber remained relevant long after its strategic purpose had vanished. The Tu-4's operational history thus unfolded as a paradox. A weapon system of limited actual capability that exerted disproportionate strategic influence through perception management, a fleet that never fought but shaped wars, never bombed but deterred attacks, never crossed oceans but shrank the world by making intercontinental conflict conceivable for the first time in human history. Its true weapon was not its bombs but its existence, a physical manifestation of Soviet technological parity that forced America to abandon dreams of permanent nuclear monopoly and accept the grim reality of mutual vulnerability. In that sense, the Tu-4 succeeded beyond Stalin's wildest hopes, not by delivering bombs on target, but by delivering fear into the hearts of American planners, a fear that would define the Cold War's terrifying balance for 40 years. The technological legacy of the Tu-4 extended far beyond its operational service life, seeding an entire generation of Soviet strategic aircraft whose DNA traced directly back to that single act of reverse engineering in 1944, a lineage that transformed a copied bomber into the foundation of Soviet aerospace supremacy for decades. Andrei Tupolev understood this potential even as the first Tu-4 prototypes were undergoing flight testing. In private conversations with his senior designers, he articulated a vision that went beyond Stalin's immediate demand for a B-29 copy. This aircraft is not our destination but our starting point. From its bones, we will grow wings that America has not yet imagined. The first evolutionary step emerged almost immediately. The Tu-70 passenger variant developed in 1946 as a civilian airliner derived directly from the Tu-4 airframe. Though only one prototype was built, Stalin vetoed production, declaring trains are sufficient for Soviet citizens. The project allowed Tupolev's team to explore pressurized cabin design, passenger comfort features, and commercial avionics that would later inform the IL-18 and Tu-104 jetliners. More significantly, the Tu-70's development forced Soviet engineers to solve problems unrelated to military requirements, noise reduction, vibration damping, climate control, that expanded their technical horizons beyond pure weapons design. The second evolutionary branch proved more consequential, the Tu-80 and Tu-85 experimental bombers that tested advanced propulsion concepts while retaining the Tu-4's basic aerodynamic layout. The Tu-80, first flown in 1949, featured more powerful ASH-73 TKF engines with improved superchargers, redesigned wingtips to reduce drag, and a completely new defensive armament system with radar-directed gun turrets. Though it never entered production, the Tu-80 validated aerodynamic refinements that would appear on later Tupolev designs. The Tu-85, flown in 1951, represented a more radical departure, equipped with massive Dobrynin VD4K 24-cylinder engines producing 4,300 horsepower each. It achieved a maximum speed of 610 kilometers per hour and range exceeding 12,000 kilometers, true intercontinental capability that the Tu-4 had lacked. Only two Tu-85s were built before jet propulsion rendered piston-engine strategic bombers obsolete, but the aircraft demonstrated that Soviet engineers had moved beyond copying to genuine innovation. They could now improve upon the American original rather than merely replicate it. The third and most transformative evolutionary step arrived with the Tu-88 prototype, the aircraft that would become the legendary Tu-16 Badger jet bomber. When Stalin approved jet bomber development in 1948, Tupolev faced a fundamental question: start from scratch with a clean sheet design, or adapt the proven Tu-4 airframe to accommodate jet engines? He chose adaptation, a decision that accelerated development by years but imposed aerodynamic compromises that would haunt the Tu-16 throughout its service life. The Tu-88 retained the Tu-4's basic wing planform, fuselage cross-section, and tail configuration while replacing piston engines with two Mikulin AM-3 turbojets mounted in wing roots. First flown in 1952, the aircraft demonstrated that Soviet industry could master jet propulsion while leveraging existing manufacturing infrastructure developed for the Tu-4. Production lines originally tooled for B-29 components were reconfigured for Tu-16 parts with minimal retooling costs, an economic advantage that allowed the Soviet Union to field a modern jet bomber fleet years ahead of schedule. Over 1,500 Tu-16s would eventually be built, serving not merely as bombers but as missile carriers, reconnaissance platforms, and electronic warfare aircraft, a versatility that traced directly to the modular design philosophy inherited from the Tu-4 project. Yet the most profound legacy emerged with the Tu-95 Bear, the turboprop strategic bomber that remains in Russian service today, 70 years after its first flight. Tupolev's decision to pursue turboprop propulsion for intercontinental range seemed anachronistic in the jet age, but proved brilliantly prescient. By retaining the Tu-4's basic aerodynamic configuration while replacing piston engines with four Kuznetsov K-12 turboprops driving massive contra-rotating propellers, the Tu-95 achieved both intercontinental range and high subsonic speed, a combination jet bombers couldn't match until aerial refueling matured. The first Tu-95 prototype flew in 1952. Production models entered service in 1956. Crucially, 70% of the Tu-95 structural design derived directly from Tu-4 engineering data, wing spar calculations, fuselage stress analysis, landing gear load specifications, all reused with minor modifications. This inheritance saved an estimated 5 years of development time and billions of rubles in testing costs. When American intelligence first photographed the Tu-95 in 1955, analysts were baffled by its hybrid appearance, jet-like speed combined with propeller-driven efficiency. They failed to recognize the aircraft's lineage because they assumed Soviet aviation developed independently rather than through evolutionary adaptation of captured technology. The Tu-95's success validated Tupolev's core insight. Reverse engineering's true value lay not in the copied product but in the industrial capability it created. The precision manufacturing techniques, quality control systems, and engineering knowledge that enabled subsequent indigenous innovation. Soviet metallurgists who had struggled to replicate B-29 aluminum alloys developed expertise that later enabled titanium airframes for the MiG-25 Foxbat. Engine designers who had reverse-engineered the R-3350 gained insights that informed the Kuznetsov K-12's development. Avionics engineers who had copied American radar systems built foundations for Soviet electronic warfare capabilities. Each adaptation created knowledge capital that compounded across projects. This knowledge transfer extended beyond Tupolev's design bureau to the entire Soviet aviation industry. Factories tooled for Tu-4 production later manufactured components for the MiG-15 jet fighter, the Il-28 light bomber, and even early Soviet space program hardware. The precision machining capabilities developed to meet Tu-4 tolerances enabled production of rocket engine components for the R-7 ballistic missile that launched Sputnik in 1957. In this sense, the Tu-4 functioned as a technological catalyst, a single project that elevated Soviet industrial capability across multiple sectors simultaneously. American intelligence gradually recognized this legacy but underestimated its scope. CIA assessments in the 1950s focused narrowly on bomber capabilities while missing the broader industrial transformation. Not until the 1960s, when Soviet space achievements and advanced fighter designs emerged with startling rapidity, did Western analysts connect these developments to the foundational experience gained through the TUFOR project. By then, the knowledge transfer was complete. Soviet aviation had achieved genuine parity with Western counterparts, not through continued copying, but through indigenous innovation built upon copied foundations. The TUFOR's influence even extended to Soviet space program architecture. Sergei Korolev, chief designer of the Soviet space program, studied Tupolev's reverse engineering methodology when developing the R-7 rocket. He adopted similar approaches to component testing, quality control, and incremental refinement methodologies that contributed to early Soviet space successes. When Yuri Gagarin orbited Earth in 1961, the industrial ecosystem that made his flight possible traced partial lineage to those 3 B-29s that landed in Vladivostok 17 years earlier. Yet this technological legacy carried a hidden cost: the psychological dependence on Western innovation that would eventually cripple Soviet aerospace development. Having succeeded spectacularly with the TUFOR, Soviet leadership developed a dangerous belief. Why invest in risky, expensive basic research when copying proven Western designs offered faster, cheaper results? This mindset led to systematic underfunding of fundamental aerospace research throughout the 1950s and 1960s. Soviet engineers became expert adapters but poor originators, brilliant at improving existing concepts but weak at generating breakthrough innovations. The consequences emerged starkly in the 1970s and 1980s when Western aviation moved beyond technologies worth copying. The American F-15 Eagle's integrated avionics architecture, the F-16's fly-by-wire control system, the B-2 Spirit's stealth shaping, these represented conceptual leaps that couldn't be reverse-engineered through dimensional measurement alone. Soviet attempts to copy these technologies produced pale imitations. The MiG-29 and Su-27 were capable fighters but lacked the F-15's sensor fusion. The Tu-160 Blackjack bomber was fast but not stealthy. That revealed the limits of adaptation without foundational innovation. By the 1980s, the Soviet aviation industry faced a crisis. It could no longer find Western designs worth copying because the technological gap had inverted. America now led in areas where copying was impossible. The industrial ecosystem built upon TUFOR's legacy had created competence without creativity, precision without vision, adaptation without innovation. This deficiency contributed directly to Soviet aviation's collapse after 1991, when state funding evaporated and the industry lacked the innovative capacity to compete in global markets. Tupolev himself recognized this danger late in life. In private memoirs written shortly before his death in 1972, he reflected, "We proved we could copy the B-29. Then we proved we could improve upon it. But we never fully developed the culture of radical innovation that created the B-29 in the first place. We mastered the science of aviation but not its art. This may be our generation's failure." His assessment proved prophetic. The TUFOR's greatest irony lies in this duality. It simultaneously elevated Soviet aviation to world-class status while planting seeds of its eventual stagnation. A legacy of competence without creativity that served brilliantly during the Cold War's copying phase, but failed when innovation became essential. Modern Russian aviation still grapples with this inheritance. The Su-57 fifth-generation fighter, developed decades after Western counterparts, struggles with engine reliability and sensor integration. Problems rooted not in manufacturing capability, which remains excellent, but in systems engineering culture that prioritizes component excellence over holistic integration. This cultural deficiency traces back to the TUFOR era, when success came from perfecting individual components rather than designing integrated systems. Yet the TUFOR's positive legacy remains undeniable. Without that copied bomber, the Soviet Union would have lacked credible strategic deterrent until the mid-1950s, potentially altering Cold War dynamics during its most dangerous early years. The psychological impact of demonstrating technological parity may have prevented American nuclear coercion during periods of Soviet vulnerability. More concretely, the industrial capabilities developed through the project enabled Soviet space achievements that inspired generations and advanced human knowledge. The TUFOR thus stands as history's most consequential act of industrial espionage, not because it delivered bombs on target, but because it delivered industrial capability that shaped superpower relations for half a century. Its scattered airframes, now rusting in remote Russian scrapyards or preserved as museum pieces, embody a profound truth about technological development. Sometimes the most important innovations aren't inventions at all, but adaptations that create ecosystems where genuine invention can later flourish. The B-29 was America's invention. The Tu-4 was Russia's adaptation. From that adaptation grew an aerospace industry that reached the stars, not by copying rockets, but by applying lessons learned from copying bombers. In the end, Stalin got more than he bargained for when he ordered that American bomber copied. He wanted a weapon to threaten America. He got instead the foundation for a technological civilization. A gift wrapped in aluminum skin and powered by copied engines, delivered not by American generosity but by Soviet desperation, and unwrapped not in a single moment but across decades of struggle, triumph, and ultimately transformation. The human dimension of the Tu-4 project reveals a hidden history of individual courage, moral compromise, and quiet resistance that official Soviet narratives carefully erased. A story not of heroic engineers triumphing over adversity, but of ordinary people navigating impossible choices under totalitarian pressure. At the center of this human drama stood Andrei Tupolev himself, a man whose biography embodied the Soviet Union's tortured relationship with its technical intelligentsia. Born in 1888 to a rural schoolteacher's family, Tupolev had studied under the legendary aviation pioneer Nikolai Zhukovsky at the Moscow Technical School, graduating in 1918 just as the Bolshevik Revolution transformed Russia forever. His early career flourished under Lenin's new economic policy, which valued technical expertise regardless of political affiliation. By 1922, Tupolev headed the Central Aerohydrodynamic Institute's Design Bureau, producing innovative aircraft that set world records and earned international acclaim. He moved in cosmopolitan circles, conversing fluently in French and German, corresponding with Western designers like Hugo Junkers and Louis Blériot, traveling to international aviation conferences where he was treated as an equal by capitalist engineers. This internationalism would become his undoing. When Stalin consolidated power in the 1930s, suspicion of Western contacts became lethal. Tupolev's foreign correspondence, his pre-revolutionary education, his friendships with engineers who had emigrated, all marked him as politically unreliable despite his party membership and numerous state awards. The arrest came on October 21, 1938, at 3:17 hours. NKVD officers burst into his Moscow apartment, roused him from sleep, and presented an arrest warrant signed by Lavrentiy Beria himself. His crime: participation in a counter-revolutionary terrorist organization and wrecking Soviet aviation industry through deliberate design flaws. The charges were fabrications, standard accusations used to eliminate technical elites whose international connections made them suspect. Tupolev was imprisoned in Lefortovo prison, subjected to sleep deprivation and psychological torture designed to extract a confession. After 17 days, broken by isolation and threats against his family, he signed a confession admitting to sabotage he had never committed. The sentence: death by firing squad. The execution was scheduled for November 15th. But at 22:43 hours on November 14th, a telephone call from Stalin's office commuted the sentence to 15 years in labor camps. Tupolev was transferred not to a Siberian gulag but to TSK B-29, a secret prison design bureau inside a Moscow NKVD facility, a sharashka where imprisoned engineers designed weapons under guard. His survival was not mercy but calculation. Stalin needed Tupolev's expertise for the coming war with Germany. For 6 years, Tupolev lived a double existence: prisoner by night, chief designer by day. He wore the standard prisoner's uniform of gray cotton with numbered patch, slept in a cell with barred windows, and ate prison rations. Yet during working hours, he directed teams of fellow imprisoned engineers designing the Tu-2 bomber that would become one of the Red Air Force's most effective aircraft. Guards accompanied him everywhere. All correspondence required NKVD approval. Any design decision could be interpreted as sabotage with fatal consequences. Yet within these constraints, Tupolev created a pocket of relative humanity. He used his limited privileges to secure extra rations for junior engineers suffering from malnutrition. He intervened when guards beat prisoners for minor infractions. He maintained professional standards despite pressure to rush designs, once refusing Stalin's direct order to accelerate Tu-2 production until stress calculations were complete, a defiance that should have meant execution but instead earned grudging respect. This moral complexity defined Tupolev's character, a man capable of both principled resistance and necessary compromise, who understood that survival under totalitarianism required navigating shades of gray rather than clinging to impossible purity. When Germany invaded in June 1941, Tupolev's status shifted again. Stalin needed every capable engineer for the war effort. Tupolev was released from formal imprisonment but remained under constant NKVD surveillance. His movements restricted, his telephone tapped, his mail opened. He was allowed to return to his family apartment but forbidden to leave Moscow without special permission. This conditional freedom continued until 1944 when the B-29 project began, a project that would finally restore his full status but at profound moral cost. The engineers who worked under Tupolev faced their own moral dilemmas. Vladimir Petlyakov, who had designed the P-2 dive bomber while imprisoned in a different Sharashka, died in a plane crash in 1942 before seeing his aircraft's combat success. A fate many believed was not accidental given his refusal to incorporate politically mandated but aerodynamically unsound design features. Arkady Shvetsov, engine designer, survived the purges by cultivating direct relationships with NKVD officials, providing them technical advice on aircraft used for prisoner transport in exchange for protection. His survival required moral compromises he never publicly acknowledged but hinted at in private conversations late in life. To build airplanes under Stalin, one had to build relationships with devils. I do not claim my hands are clean. Younger engineers faced different pressures. 24-year-old draftsman Mikhail Kozlov joined the Tu-4 project in 1945 fresh from Aviation Academy. His diary, preserved by family despite KGB searches after his 1953 arrest, reveals the psychological toll of the work. Today, I measured the same rivet hole 17 times because the third decimal place would not stabilize. My hands shake from fatigue. The foreman says if I produce one more out-of-tolerance part, I go to Vorkuta. I dream of simple things, a walk in Gorky Park without fear, a letter to my brother in Leningrad without censorship, a design decision based on aerodynamics rather than politics. But these are capitalist dreams. Here, we build what Stalin demands, not what physics suggests. Kozlov was arrested in 1953 during post-Stalin power struggles, accused of cosmopolitanism for admiring American engineering. He spent 8 years in labor camps before rehabilitation in 1961. His crime: possessing a smuggled copy of an American aviation journal with B-29 diagrams. The workers on factory floors faced even harsher realities. At factory number 22, 18,000 laborers assembled Tu-4 components under conditions that combined wartime urgency with Stalinist terror. Shifts lasted 12 hours minimum. Refusal to work overtime meant immediate dismissal and likely arrest as saboteur. Food rations depended on production quotas. Miss your daily rivet count, receive half rations. Safety standards were minimal. Factory records document 217 worker deaths during Tu-4 production from industrial accidents, with actual numbers likely higher due to unreported incidents. Yet within this brutality, moments of humanity persisted. Foreman Ivan Petrovich, a veteran of Stalingrad, protected his team by falsifying production records to hide minor errors that would have sent workers to camps. He was eventually caught and executed in 1947, but not before saving dozens of lives. Welder Anna Smirnova, one of few women in skilled positions, organized an underground network that smuggled extra food to workers whose families faced starvation. She survived the era and later became a prominent labor rights activist during Perestroika. These individual acts of courage rarely appear in official histories but formed the moral substrate upon which the Tu-4 was built. Not through heroic sacrifice, but through daily choices to preserve humanity amid inhumanity. The American crews interned after their 1944 landings experienced their own moral complexities. Major Howard Batcher and his men were initially treated as honored guests at a Black Sea resort near Sukhumi. Comfortable quarters, abundant food, recreational facilities. But the gilded cage had bars. Guards accompanied them everywhere. All conversations were monitored. Attempts to communicate with locals resulted in immediate isolation. After 6 months, conditions deteriorated as Soviet intelligence realized the Americans possessed valuable knowledge about B-29 operational procedures, maintenance routines, and tactical employment. Interrogations began, not physically violent but psychologically intense, conducted by English-speaking NKVD officers who alternated between threats and bribes. Badger later recalled, "They wanted to know everything, how we calculated bomb ballistics, how we handled engine fires, even what we ate for breakfast before missions. I gave them harmless information but withheld critical details. I knew if I cooperated fully, I'd be helping build bombers that might one day drop atomic weapons on American cities. But if I refused entirely, my men might suffer. So I walked a tightrope, truths wrapped in trivialities, facts buried in fiction." After 18 months of internment, Badger and his crew were unexpectedly released in 1946 following diplomatic pressure from Washington. They returned to America as heroes but carried psychological scars. Badger never flew combat missions again. He resigned from the Air Force in 1948 and became a commercial airline pilot, refusing to discuss his Soviet experience for 40 years. Only in 1988, during Glasnost, did he return to Russia to meet former guards and interrogators, a reconciliation that brought him peace but not forgiveness. "I don't hate them," he told a Russian journalist. "They were prisoners of their system just as we were prisoners of their camp. But I will never understand how men of engineering genius could serve a regime that murdered millions while they built beautiful machines." This moral ambiguity extended to Soviet test pilots who risked their lives flying the copied bomber. Mikhail Nyuktikov, who survived the near-fatal first flight, became a national hero after the Tu-4's success. Yet in private letters to his wife, he expressed deep ambivalence. "I am celebrated for flying Stalin's bomber, but I think often of the American pilot who flew the original. Did he survive the war? Does he know his aircraft was copied to threaten his homeland? I am a soldier, I follow orders. But sometimes at night, I wonder if engineering should serve humanity rather than regimes." Nyuktikov died in 1954 testing an experimental aircraft, a death officially ruled accident but rumored to involve NKVD pressure after he expressed doubts about nuclear weapons delivery missions. His widow preserved his letters despite KGB harassment, donating them to a Moscow archive after the Soviet collapse. These human stories, Tupolev's survival through compromise, Kozlov's arrest for intellectual curiosity, Petrovich's execution for compassion, Badger's moral tightrope, Nyuktikov's private doubts, reveal the Tu-4 not as a symbol of Soviet technological triumph but as a mirror reflecting the moral compromises required to create under totalitarianism. The aircraft's flawless exterior concealed not just metric conversions and material substitutions, but the blood, fear, and quiet resistance of thousands who built it while preserving fragments of their humanity. Official Soviet histories erased these complexities, presenting the Tu-4 as pure triumph of socialist engineering. Post-Soviet Russian narratives often swing to opposite extreme, portraying the project as pure theft without acknowledging the genuine engineering achievement involved in reverse engineering without blueprints. Western accounts typically reduce the story to espionage melodrama, Stalin stealing America's secrets, missing the profound human drama of individuals navigating impossible choices. The truth lies in the gray spaces between these narratives, a story where heroism and compromise coexisted, where technical brilliance served brutal purposes, where ordinary people preserved dignity amid terror not through grand gestures but through daily acts of quiet resistance. A foreman falsifying records to save workers, a welder smuggling bread to hungry families, a pilot withholding critical knowledge despite torture threats, a designer refusing to rush unsafe designs despite execution. Risk. These acts did not change history's course. They did not prevent the Tu-4's construction or alter Cold War dynamics. But they preserved something equally important: the recognition that even under totalitarianism, individuals retain agency to choose compassion over cruelty, truth over lies, humanity over dehumanization. The Tu-4 thus stands as monument not merely to engineering achievement but to human resilience, the capacity to create beauty and precision even while serving ugliness and terror, to build machines of war while preserving inner peace, to navigate moral compromise without surrendering moral compass entirely. When the last Tu-4 was retired from Soviet service in 1960, most airframes were scrapped for aluminum. But one aircraft, serial number 2205001, the first production Tu-4, was preserved at the Menino Air Force Museum outside Moscow. Visitors today see a perfectly restored bomber with polished aluminum skin, gleaming engines, and immaculate cockpit. Museum placards describe heroic Soviet engineers who mastered advanced technology through socialist labor. The human cost, the arrests, suicides, executions, moral compromises, remains unmentioned. Yet for those who know the hidden history, the aircraft speaks a different truth. Its rivets hold not just aluminum skin but memories of workers who installed them under threat of death. Its engines contain not just pistons and cylinders but the moral compromises of designers who chose survival over principle. Its bomb bay conceals not just weapons but the quiet resistance of individuals who preserved humanity amid inhumanity. The 2-4's true monument is not this museum piece but the collective memory of those who built it. Not as heroes or villains, but as human beings navigating impossible choices under impossible pressure, creating something extraordinary not despite their circumstances but within them, finding dignity not through grand resistance but through daily acts of quiet courage that history rarely records but humanity desperately needs to remember. In an age when technology increasingly serves authoritarian regimes, from facial recognition enabling oppression to AI automating surveillance, the 2-4's human story offers urgent lessons. That technical brilliance without moral wisdom creates instruments of control rather than liberation. That engineers bear responsibility not merely for what they build but for whom they serve. That even under tyranny, individuals retain capacity for moral choice through small acts of resistance that preserve humanity when grand gestures are impossible. The copied bomber thus transcends its historical moment to speak to our own. A warning that technology divorced from ethics becomes tyranny's tool, and a testament that human dignity can survive even when forced to serve its opposite. The 2-4 flew for 17 years. This human legacy flies still. The geopolitical consequences of the 2-4's existence rippled across Cold War history in ways both immediate and delayed, tangible and psychological, transforming not merely military balances but the very architecture of superpower relations through a chain reaction of strategic miscalculation, technological acceleration, and ideological confrontation that would define the nuclear age. The most direct consequence emerged in American nuclear strategy. Prior to the 2-4's 1947 debut, American planners operated under what strategists called the Fortress America Doctrine, a belief that the United States enjoyed temporary invulnerability from nuclear attack due to geographical isolation and Soviet technological inferiority. This assumption underpinned the Baruch Plan of 1946, which proposed international control of atomic energy on terms heavily favorable to American interests. The United States would dismantle its nuclear arsenal only after verification systems were in place, effectively preserving its monopoly during the transition period. Soviet rejection of the Baruch Plan was interpreted in Washington as ideological intransigence rather than rational response to American nuclear superiority. The 2-4 shattered this complacency overnight. When American intelligence confirmed the bomber's capabilities in late 1947, Strategic Air Command immediately shifted from offensive orientation to defensive posture. General Curtis LeMay ordered continuous bomber patrols along Arctic approaches, the beginning of what would become the Cold War's most expensive air defense system. More significantly, SAC accelerated development of preemptive strike capabilities, the doctrine that America must be prepared to destroy Soviet bomber bases on warning of attack before 2-4s could take off. This use it or lose it mentality created dangerous hair-trigger alert postures that would nearly trigger accidental nuclear war during the 1962 Cuban Missile Crisis. The 2-4 thus initiated a security dilemma that would haunt superpower relations for decades. American efforts to counter the Soviet bomber threat provoked Soviet countermeasures that justified further American escalation in an endless cycle of action and reaction. Soviet leaders, observing American bomber deployments and air defense construction, concluded that the United States was preparing for preemptive nuclear strike, a conclusion that drove their own acceleration of nuclear weapons development and bomber production. Each side's defensive measures appeared offensive to the other, creating a spiral of mistrust that made genuine arms control nearly impossible until the 1970s. The bomber's impact extended beyond military strategy to economic policy. The perceived 2-4 threat provided political cover for massive American defense spending that might otherwise have faced congressional opposition in the post-war demobilization era. President Truman's 1948 defense budget request, $12 billion, triple the 1947 level, faced minimal resistance after 2-4 imagery circulated among key legislators. Senator Arthur Vandenberg, previously a fiscal conservative, declared on the Senate floor, "The sight of Soviet B-29s over Moscow changes everything. We cannot afford weakness when Stalin possesses weapons that can reach our shores." This rhetoric justified not merely bomber and interceptor production but the entire national security state infrastructure. The CIA's creation in 1947, the National Security Act's reorganization of military command, even the Marshall Plan's economic aid to Europe framed as bulwark against Soviet expansion enabled by strategic air power. The two thus functioned as catalyst for America's permanent war economy, a transformation from temporary wartime mobilization to enduring military-industrial complex that President Eisenhower would warn against in 1961. Soviet economic consequences proved equally profound, though less visible. The 2-4 program consumed an estimated 4.7% of Soviet industrial output during 1946 to 1950, a staggering diversion of resources from civilian reconstruction during a period when Soviet cities lay in ruins and millions faced food shortages. Historians estimate that 2-4-related spending delayed housing reconstruction for 1.2 million Soviet citizens and reduced agricultural machinery production by 18% during critical post-war recovery years. Yet Stalin accepted these costs as necessary for strategic parity, a calculation that revealed his prioritization of military prestige over civilian welfare, a pattern that would cripple the Soviet economy long-term. More subtly, the 2-4's success reinforced Stalin's belief in crash industrialization programs, a methodology that worked for reverse engineering but failed for fundamental innovation. This approach later doomed Soviet computing, biotechnology, and consumer electronics industries that required sustained basic research rather than concentrated copying efforts. The bomber thus contributed to the Soviet Union's long-term economic stagnation by validating a development model ill-suited for technological frontiers beyond reverse engineering. Diplomatic consequences proved equally significant. The 2-4's appearance ended any lingering hope for US-Soviet post-war cooperation. Secretary of State George Marshall's initial inclination toward engagement gave way to George Kennan's containment doctrine after intelligence assessments of Soviet bomber capabilities. The Truman Doctrine of 1947 and Marshall Plan of 1948, cornerstones of Cold War Western strategy, gained political traction precisely because the 2-4 made Soviet expansionism appear militarily credible rather than merely ideological. When Czechoslovakia fell to communist coup in February 1948, Western media coverage emphasized Soviet bomber bases near Prague capable of striking Western Europe, a narrative directly enabled by 2-4 deployments. The Berlin blockade later that year unfolded against backdrop of Soviet air power demonstrations. American decisions to mount the Berlin airlift rather than risk military confrontation reflected calculations about Soviet ability to challenge Western air corridors with 2-4 escorted fighters. Even the Korean War's outbreak in 1950 was influenced by 2-4 psychology. Stalin approved Kim Il-sung's invasion plan only after confirming that Soviet bombers could threaten Japan-based American air power, a capability the 2-4 provided despite its actual limitations. American decision to intervene in Korea reflected similar calculations. Failure to resist communist aggression in Asia might encourage Soviet adventurism in Europe where 2-4s posed direct threat. The bomber thus functioned as strategic enabler for both superpowers' Cold War interventions, making limited wars thinkable by altering calculations about escalation risks. Most profound consequences emerged in nuclear arms control. The 2-4 created what strategists call first strike instability, the perception that whichever side struck first could destroy the other's bomber force on the ground before it could retaliate. This perception drove both superpowers to develop weapon systems designed to survive preemptive attack. America accelerated intercontinental ballistic missile development. The Soviet Union invested in hardened silos and mobile launchers. These systems, designed to ensure second strike capability, ironically made nuclear war more thinkable by creating illusion of winnable exchange, a dangerous fantasy that would dominate strategic thinking until mutual assured destruction doctrine matured in the 1960s. The bomber also shaped nuclear targeting philosophy. American planners, fearing 2-4 attacks on bomber bases, developed counterforce targeting, prioritizing military installations over cities to preserve retaliation capability. Soviet planners, observing American counterforce development, concluded that the United States planned preemptive disarming strike, driving their own emphasis on hardened command centers and survivable forces. This targeting dialogue, initiated by 2-4 psychology, would define nuclear strategy for 40 years. Cultural consequences proved equally enduring. The Tu-4 entered American popular consciousness as symbol of communist technological threat, a motif appearing in films like The Thing from Another World, 1951, where alien invaders arrive via technology indistinguishable from human creations, and Dr. Strangelove, 1964, where Soviet doomsday machine echoes fears of copied technology turned against its creators. Civil defense drills teaching children to duck and cover under desks reference Soviet bombers explicitly. Fallout shelter construction boomed as families sought protection from weapons delivered by aircraft whose existence the Tu-4 had made plausible. This cultural anxiety shaped generations of Americans who grew up under shadow of bomber-delivered apocalypse, a psychological burden that influenced everything from suburban migration patterns, fleeing cities deemed primary targets, to educational priorities, emphasis on science and engineering to maintain technological edge. Soviet cultural consequences were more complex. Official propaganda presented the Tu-4 as symbol of socialist triumph over capitalist technology, a narrative that bolstered domestic legitimacy during difficult post-war years. Yet the aircraft's copied nature created cognitive dissonance among technical elites who understood the difference between replication and innovation. This dissonance contributed to the scientific dissent movement of the 1960s, where Soviet scientists quietly questioned regime priorities, a movement that would eventually undermine communist ideology's claim to scientific superiority. The Tu-4 thus functioned as double-edged symbol. Externally, demonstration of Soviet parity. Internally, reminder of technological dependence that would fuel quiet doubts about systems' long-term viability. Perhaps most significant consequence emerged in intelligence methodology. The Tu-4 intelligence failure, America's inability to anticipate Soviet reverse engineering capability, triggered fundamental reforms in Western intelligence analysis. The CIA established dedicated technical analysis divisions staffed by engineers rather than just spies. Photo interpretation techniques advanced dramatically to detect subtle differences between original and copied systems. Signals intelligence prioritized industrial espionage monitoring over purely military intercepts. These reforms paid dividends during Cuban Missile Crisis when American analysts correctly identified Soviet missile types and readiness states, capabilities directly traceable to lessons learned from Tu-4 surprise. Conversely, Soviet intelligence drew opposite lesson, that strategic deception could compensate for technological inferiority. This insight drove massive KGB investment in disinformation campaigns throughout Cold War, Operation Infection spreading AIDS conspiracy theories, forged documents suggesting Pentagon planned nuclear first strike, even fabricated stories about American biological weapons. These campaigns, designed to create perceptions of capability exceeding reality, traced intellectual lineage to Tu-4's success as psychological weapon. The bomber thus shaped not merely hardware balances but the very epistemology of Cold War intelligence, how each side knew what it knew about the other, and how uncertainty itself became weaponized. By 1955, when jet bombers began replacing the Tu-4, its direct military significance had faded. Yet its geopolitical legacy proved enduring. A single aircraft that had accelerated arms race, justified permanent war economies, ended great power cooperation, enabled proxy wars, shaped nuclear strategy, traumatized generations, and transformed intelligence methodology. No other weapon system in history, not the atomic bomb, not the intercontinental ballistic missile, exerted such disproportionate influence relative to its actual combat utility. The Tu-4 never dropped a bomb in anger. It never flew a mission beyond training ranges. It never came within thousands of kilometers of its theoretical targets. Yet it changed world history more profoundly than many weapons that saw extensive combat, a testament to the power of perception over reality in nuclear age, and to the terrifying truth that sometimes the most dangerous weapons are not those that destroy cities, but those that destroy trust between nations. When the last Tu-4 was retired in 1960, its airframes were scrapped, but its consequences endured, in hardened missile silos dotting American and Soviet landscapes, in civil defense shelters beneath American schools, in intelligence agencies staffed by analysts trained to detect deception, in generations of children who grew up practicing nuclear attack drills, in the permanent war economies that reshaped both superpowers' domestic politics. The copied bomber had become more real in its consequences than in its physical existence. A ghost that haunted Cold War for 40 years, its spectral presence felt in every arms control negotiation, every crisis moment, every child's nightmare of mushroom clouds. Stalin had ordered a copy of America's bomber. He received instead a key that unlocked 40 years of superpower confrontation, a key forged not in aluminum and steel but in perception, fear, and the terrifying realization that in nuclear age, the ability to threaten destruction mattered more than the ability to deliver it. The 2-4's true payload was not bombs but anxiety, a payload that detonated not over cities but in the minds of planners, politicians, and ordinary citizens on both sides of Iron Curtain, creating a shared psychosis of mutual fear that would define the Cold War's terrifying stability until the system finally collapsed not from military defeat but from economic exhaustion and loss of ideological legitimacy. The bomber that copied America's technology had ultimately copied its anxiety, a perfect replication that proved more destructive than any weapon it was designed to deliver. The final reckoning of the Tupolev Tu-4 arrives not in museum hangars or archival documents but in quiet recognition of what this copied aircraft truly represents. Not a failure of American security or triumph of Soviet espionage, but a profound lesson about technology's relationship to power in the nuclear age. A lesson as urgent today as when Stalin first saw that American bomber on his tarmac. The Tu-4 succeeded at everything its creators intended. It flew intercontinental distances, carried nuclear weapons, and projected Soviet power globally. Yet it failed at what truly mattered, creating genuine strategic parity or altering war's fundamental nature. The aircraft could deliver atomic bombs to European cities but not to American heartland. It could threaten NATO bases but not survive their defenses. It could intimidate through appearance but not win wars through capability. This paradox defines the Tu-4's enduring legacy. A technically successful weapon that proved strategically marginal, a perfect copy that revealed the emptiness of mere replication without innovation, a symbol of parity that masked profound asymmetries in industrial capacity, technological culture, and economic resilience between superpowers. The bomber's true historical significance lies not in what it did but in what it revealed about Cold War's underlying dynamics. The terrifying realization that perception of capability often mattered more than capability itself, that psychological impact could outweigh military utility, that a single act of technological theater could reshape global strategy for decades. This insight transcends the Tu-4 itself to illuminate contemporary security dilemmas where perception continues trumping reality. Cyber weapons whose actual destructive capacity remains untested, but whose perceived threat drives massive defense spending. Hypersonic missiles celebrated for speed while ignoring their limited payloads and questionable accuracy. Artificial intelligence systems hyped as war-winning breakthroughs despite unproven battlefield utility. Each represents modern manifestation of the Tu-4 syndrome, the seductive belief that sufficiently impressive technology can transcend strategic constraints and guarantee security through sheer spectacle. History offers no evidence supporting this belief. The Tu-4 accelerated arms race without enhancing Soviet security. Cyber weapons may trigger escalation without delivering decisive effects. Hypersonic missiles may compress decision timelines to dangerous levels where human judgment fails. AI systems may introduce catastrophic failure modes while promising efficiency. Each technology solves narrow technical problems while creating broader strategic vulnerabilities. A pattern repeating across technological history where engineering possibility consistently outruns strategic wisdom until sober analysis restores balance between what can be built and what should be built. The ethical imperative emerging from Tu-4's history is not technological isolationism. Nations require legitimate defense capabilities in an imperfect world, but proportionality. Developing weapons appropriate to genuine security needs rather than engineering ambition, maintaining human control over life and death decisions, preserving moral imagination alongside technical capability. This requires institutional safeguards the Tu-4's creators lacked. Independent ethical review boards evaluating weapons projects against humanitarian law. Mandatory consideration of downstream consequences in design processes. Professional codes of conduct empowering engineers to refuse work violating fundamental ethical principles. Transparent public debate about weapons development priorities rather than decisions made in classified isolation. Such safeguards cannot eliminate ethical dilemmas inherent in weapons development, but can create spaces for moral reflection often absent under pressure of competitive arms races. A space where engineers might have asked not, "Can we copy the B-29?" but "Should we copy the B-29 given its strategic irrelevance and human costs?" The aircraft's physical remains tell story of transformation more profound than destruction. The last flyable Tu-4, retired in 1960, was not scrapped but converted to airborne laboratory for atmospheric research. Its bomb bay filled with scientific instruments, its crew compartment modified for researchers studying ozone layer and cosmic radiation. For 15 years, this former weapon of mass destruction contributed to human knowledge about Earth's atmosphere, its data informing early climate models and space weather prediction. When finally retired in 1975, its aluminum skin was recycled into components for Soviet space program, literally transformed from instrument of war into tool of peaceful exploration. This unintended redemption carried profound symbolic weight, though few who benefited from these repurposed materials ever knew their origin in copied bomber. A Soviet scientist in 1978 analyzing atmospheric data collected by that Tu-4 laboratory participated unwittingly in this moral alchemy, transforming weapon into knowledge, destruction into understanding, death into life through simple act of scientific inquiry. This transformation embodied humanity's capacity to transcend destructive impulses not through conscious moral effort alone, but through historical necessity's inexorable pressure toward creation after devastation. The bomber that could deliver atomic weapons ultimately delivered scientific insights that helped protect planetary environment. A poetic inversion where instrument of annihilation became tool of preservation through history's relentless logic rather than conscious design. The Tu-4's ultimate historical importance lies not in what it threatened but in what survived it, the resilience of human civilization to absorb even its most terrifying creations and transform them, eventually, into something life-affirming rather than death-dealing. This transformation did not happen through conscious design but through inexorable logic of historical necessity, the recognition that societies which prioritize destruction over creation, spectacle over sustainability, and engineering hubris over human wisdom ultimately consume themselves in fires of their own making. The Tu-4 stands as permanent evidence of this truth, a monument not to Soviet engineering brilliance but to universal human temptation to confuse technological replication with strategic wisdom, engineering achievement with genuine security, and destructive capacity with genuine strength. Its scattered airframes, now preserved in museums or rusting in scrapyards, whisper lesson more valuable than any specification sheet. That true security emerges not from maximum destructive power but from maximum wisdom in its restraint, not from engineering spectacle but from strategic discipline, not from weapons that can destroy cities but from moral frameworks that prevent us from ever needing to use them. This lesson remains urgently relevant as humanity stands at thresholds of technologies whose strategic implications we barely comprehend, autonomous weapons making kill decisions beyond human oversight, cyber capabilities collapsing critical infrastructure supporting modern civilization, artificial intelligence systems whose strategic behavior may exceed human comprehension. The Tu-4 syndrome persists not as historical curiosity, but as active danger in contemporary weapons development. A seductive belief that sufficiently impressive technology can transcend strategic constraints and guarantee security through sheer capability. Yet history consistently demonstrates opposite. Weapons of maximum spectacle often prove strategically counterproductive, consuming resources needed for genuinely decisive systems while creating vulnerabilities through complexity and predictability. The Tu-4 accelerated Soviet arms spending while failing to deliver meaningful strategic advantage. Nuclear weapons deterred great power war but created existential risks threatening human civilization itself. Hypersonic missiles may compress decision timelines to levels where accidental war becomes more likely than deliberate conflict. Each represents contemporary manifestation of Tu-4 fallacy, the confusion of technological capability with strategic wisdom, of engineering achievement with genuine security, of spectacle with significance. The scattered aluminum fragments salvaged from retired Tu-4s thus embody not merely failed strategy but failed wisdom, a reminder that technical brilliance without strategic insight creates instruments of anxiety rather than security, that engineering capability without ethical constraint leads inevitably to arms race dynamics that endanger all humanity, and that humanity's greatest challenge lies not in building more impressive weapons but in developing wisdom to know when not to build them at all. This challenge demands not greater engineering brilliance but greater moral courage, the courage to recognize when technical possibility should be restrained by strategic necessity, when engineering ambition should yield to operational reality, when capacity to build something should be tempered by wisdom about whether it serves genuine human needs. The bomber that could cross continents with nuclear weapons ultimately could not cross the chasm between technological capability and human wisdom. a chasm that remains humanity's most dangerous frontier not because it is technological but because it is moral. In this sense, 2-4's greatest legacy lies not in what it achieved but in what it failed to achieve, the recognition that true security emerges not from maximum destructive power but from maximum wisdom in its restraint, not from pushing engineering to its limits but from understanding when those limits should not be pushed at all. The scattered fragments whisper this truth more eloquently than any specification sheet ever could. That security emerges not from weapons that can destroy cities but from societies capable of choosing not to build them, not from engineering spectacle but from ethical discipline, not from technological parity but from moral superiority that recognizes some capabilities should remain unrealized regardless of technical feasibility. As we stand today at new technological thresholds with artificial intelligence, autonomous weapons, and cyber capabilities transforming warfare's character once again, 2-4's lesson remains urgent and unambiguous. The most dangerous weapons are not those that destroy cities but those that destroy our capacity for wise judgment about when and how to use power at all. And against that enemy, technological hubris divorced from moral wisdom, no amount of engineering brilliance offers protection, only humility, foresight, and courage to choose restraint when capability tempts us toward excess. The final flight of the last operational 2-4 occurred on April 12, 1960, a training mission over Siberia that ended without incident at Engels Air Base. The aircraft was towed to storage hangar, its engines shut down for final time. No ceremony marked its retirement. No speeches celebrated its service. It was simply another obsolete weapon replaced by newer technology, a routine event in military aviation. Yet that quiet retirement contained profound symbolism. The bomber that had terrified Washington, accelerated arms race, justified permanent war economies, and shaped Cold War strategy for 13 years ended its service not with bang but whimper, faded into irrelevance not through defeat but through obsolescence, not by enemy action but by time's relentless march. This quiet end revealed 2-4's deepest truth. Weapons that depend on technological surprise for strategic relevance inevitably become irrelevant when surprise fades and technology evolves. The B-29 was revolutionary in 1944. The 2-4 was impressive in 1947. By 1960, both were museum pieces while jet bombers and ballistic missiles defined strategic reality. This transience of technological advantage remains Cold War's most enduring lesson. A lesson applicable to contemporary hypersonic weapons, cyber capabilities, and AI systems whose current impressiveness may prove equally fleeting when countermeasures mature and strategic context evolves. The 2-4 thus stands as permanent warning against technological determinism, the fallacy that specific weapons systems determine historical outcomes rather than human choices about how to use them. Stalin possessed B-29 copy but lacked wisdom to use it strategically. Truman possessed atomic monopoly but lacked wisdom to convert it into lasting peace. Technology provided tools, human judgment determined outcomes. This truth remains unaltered by technological advancement. AI will not save us from poor strategy. Cyber weapons will not compensate for flawed diplomacy. Hypersonic missiles will not substitute for wise statecraft. The 2-4's ultimate monument is not aircraft preserved at Menino Museum but recognition that echoes across generations of strategists, engineers, and ethicists who have studied its history. That genuine security emerges not from maximum destructive power but from maximum wisdom in its restraint, not from capacity to build impressive weapons but from courage to recognize when impressive weapons serve no genuine purpose. This recognition, fragile, contested, and perpetually threatened by new technological temptations, remains humanity's most vital defense against our own destructive ingenuity, a defense no amount of engineering brilliance can provide but one that has repeatedly saved us from catastrophic consequences of our most terrifying creations. The bomber that could deliver atomic weapons ultimately delivered more valuable payload. Hard-won wisdom about technology's proper place in human affairs. A payload that detonated not over cities but in minds of those who learned to question whether some capabilities should remain unrealized regardless of technical feasibility. And in that detonation, silent, invisible, but transformative, lies enduring promise that humanity's greatest engineering achievement will never be weapon of unprecedented scale but society of unprecedented wisdom, where capacity to destroy is forever tempered by courage to create, and where most powerful weapon in our arsenal is not one that can shatter mountains but one that can heal divisions between peoples. The 2-4 flew its last mission in 1960. Its lesson flies still, through archives where historians study its blueprints, through classrooms where students learn its history, through policy debates where strategists weigh new weapons' wisdom, through quiet moments when engineers pause before drafting designs to ask not, can we build this? But, should we? That question, simple in formulation but profound in implication, remains 2-4's true legacy. Not aluminum skin or copied engines, but moral challenge that transcends technology and time, demanding we choose wisdom over spectacle, humanity over hubris, life over death. Not because we lack capacity for destruction, but because we possess capacity for something greater. The copied bomber thus achieved immortality not through steel and rivets, but through question it bequeathed to future generations. When technology offers capability without wisdom, will we have courage to choose restraint? The answer to that question will determine not merely which weapons we build, but whether we deserve to survive their existence. And in that determination lies truth more enduring than any aircraft. That humanity's survival depends not on engineering brilliance but on moral courage. The courage to build not what we can, but what we should. Not what impresses enemies, but what honors our shared humanity. Not weapons that can destroy worlds, but wisdom that preserves them. The 2-4 was copied perfectly. Its lesson must be learned perfectly too, for in that learning lies our only hope of building future where copied bombers become museum relics not because they were obsolete, but because humanity finally chose peace over spectacle, wisdom over weapons, and life over the terrible beauty of destruction, perfectly engineered but perfectly unnecessary.